In this video, I aim to explore some examples of gamma ray transition multipolarities and how to determine them. This applies to nuclear physics, specifically looking at transitions between different nuclear states. In addition, we will try to predict which transition will be the most intense. Many of the components of this video will rely on quantum mechanical spin addition, which relates to one of my other videos on tetraquark supermultiplet combinations. I will begin with an example and go straight through and apply rules as we go along as and when needed, rather than introducing the theory first. And then hopefully you can pick up the theory from the example. So the first example is a transition from a 2+ state to a 1- state. You should be fairly comfortable knowing that these are the nuclear spin parity states, which correspond in nuclear terms to I pi, where I is the total angular momentum of the nucleus and pi is the parity, which is different to the particle physics convention, which is usually written as J+. So we wish to understand what values of L, the change in spin, or I think the spin carried by the photon, the angular momentum carried by the photon, that gives us a transition from a 2+ to a 1+ state. Naively, you may consider L equals 1 from 2 - 1, but because this is quantum mechanics, we have to consider the spin addition formulae, which will give us an array of L. We can write the transition as going from some state B to some state A. Therefore, B subtract some L gives us A, and therefore A plus L is B. The reason why I write it in this format particularly is because I think this is exactly how the spin addition formula is usually written, as L1 plus L2 equals L total, whereas this may not be immediately intuitive in the quantum mechanical world. Therefore, we can write out 1 plus L equals 2, and now we try the various values of L until we no longer produce a 2+ state. It should be noted immediately that L equals 0 transitions, which correspond to monopole radiation, are entirely forbidden. So we will firstly consider the L equals 1 transition. This gives us 1 plus 1, these are all quantum mechanical spin states by the way, which will give us from 2, i.e. 1 plus 1, to the modulus of 1 minus 1, which is 0, in integer steps. So there is only 1 in the middle, which is 1. So an L equals 1 transition gives us these possible states. And we have the 2 that we're looking for from the B. This means that L equals 1 is a possible transition. Equally, we can consider the L equals 2 state. 1 plus 2 gives us a maximum of 3. 1 minus 2 is minus 1, and the modulus of minus 1 is 1, and there is only one integer between 3 and 1, which is 2, and again we have the 2 state. You can already see a pattern here pretty easily, that if we continue going, we're going to get 4, 3, 2, because the modulus of 1 minus 3 is 2, and the maximum is 4, and then after this, we will no longer have the initial state I equals 2. This means that for the transition 2+ to 1-, the only possible values of L are 1, 2, and 3. Now to consider the multipolarities, we must also consider the parity, and in this case, there is a parity change from plus to minus. We can write out all the gamma ray transition multipolarities as a table of sorts, where we arrange the fastest transitions on the left, going to the slowest transitions on the right, and we categorize them into groups where there is a parity change, starting with yes, there is a parity change, no, there is not a parity change, to yes, no, yes. The corresponding multipolarities that fit in these groups are E1, E2, E3, E4, and E5, electric transitions, and M1, M2, M3, and M4, magnetic transitions, where you can see E2 and M1 have comparable transition rates, as does E3 and M2, E4 and M3, E5 and M4, and so on, with E1 being the fastest. So noting that there is a parity change, we can only consider groups where we say yes, there is a parity change, and now we must find the corresponding E or M transitions that have the correct L. In this case, we consider L equals 1, 2, and 3, so therefore E1 is a valid transition, E3 is a valid transition, M2 is a valid transition, and that completes our set. Now if we want to consider which transition will be the most intense, it will of course be E1 because it has the highest and most fast transition rate. I understand this might be a little bit complicated. Spin addition can always be a little intense, especially when considering other multipolarities. So we will now consider another example, which is a 3 of a 2+ state to a 3 of a 2+ state. Initially when I saw this for the first time, I thought, that can't be right because there's no change in I. However, because of the spin addition formula and how quantum mechanical spin works, this is a possible transition. So again, we're going to consider all values of L which have 3 over 2 plus L is equal to 3 over 2. Again, L equals 0 is not a transition, it is forbidden. If we consider 3 over 2 plus 1, we get 5 over 2 to 3 over 2 minus 1, which is 1 over 2 in steps of, in integer steps. So there is a 3 over 2 state in the middle, and we have our 3 over 2 state. So L equals 1 is a possible transition. For L equals 2, we can consider 3 over 2 plus 2, which will give us 7 over 2, to 3 over 2 minus 2, which would be minus a half, but it's modulus of minus a half. So that gives us a half in steps of 1. So we have 5 over 2 and 3 over 2 in the middle. Again, the 3 over 2 state exists. Now, 3 over 2 plus 3 gives us 9 over 2. You can see that 3 over 2 minus 3 gives us minus 3 over 2. The modulus of that is 3 over 2. In integer steps, 7 over 2, 5 over 2. The great thing about writing it out like this is that you can always see that there's a pattern, and as we go up, things tend to shift right, up until you get to the point at which you start going from the modulus of positive values to the modulus of negative values, which is here, for instance. And you can see that beyond this, if we had L equals 4, we would not have the 3 over 2 state, because 3 over 2 plus 4 would give us 11 over 2, and 3 over 2 minus 4, the modulus of which is 5 over 2, which includes no intermediate 3 over 2 state. So our possible values of L are 1, 2, and 3. However, in this case, we note that there is no parity change. So going back to our table, we now consider the columns of no parity change, and that include L equals 1, L equals 2, and L equals 3, which gives us E2, M1, and M3. Now when we ask which will be the most intense transition, since E2 and M1 have comparable transition rates, we say that this is most likely going to be an M1/E2 mixed transition. By this point, I'd hope that you are starting to get a grasp on how these transitions occur, and it's really just comes down to applying the spin addition formula and calculating what values of L give you your final state. But to really be rigorous here, we will finally consider a 5 over 2 plus transition to a 1 over 2 plus transition. Therefore, 1 over 2 plus, if we consider 1 over 2 plus 1, gives us 3 over 2 to 1 over 2 minus 1, which is minus a half, but the modulus is a half. This does not include our 5 over 2 state, so L equals 1 is not a valid transition. If we consider L equals 2, have 1 half plus 2, gives us 5 over 2. 1 half minus 2 is minus 3 over 2, the modulus of which is 3 over 2, and this does include our 5 over 2 state. Next, if we consider L equals 3, we have a half plus 3 is equal to 7 over 2, and you can see the pattern here. This will go here, 5 over 2. We cannot produce a state with angular momentum less than 5 over 2 in the L equals 3 world, and you can see here that the L equals 4 world is not going to contain the 5 over 2. In fact, it's going to contain 9 over 2 and 7 over 2, which means that we can only consider L equals 2 and L equals 3 multiple transitions, and again, there is no parity change. So going back to our table, no parity change, L equals 2 and L equals 3, we have E2 and M3 transitions only. And then when we ask ourselves which one will be the fastest, E2 is much faster than M3, so this will be our transition with the greatest intensity. This concludes my short video on calculating the gamma ray transition multipolarities for a given initial and final state spin parity of a nucleus. And I hope this has been useful in developing your understanding.